The broadcast is now starting. All attendees are in listen-only mode.
Good morning, everyone, and welcome to Nautel in Halifax, Nova Scotia, Canada. We have a presentation today on the NXSeries of transmitters, high-power medium-wave transmitters. This presentation is going to be focused on the international audience. We're going to focus on transmitters that are 100 kilowatts and above, and we have a great group of presenters with us here today. I'm Chuck Kelly, Director of Sales for Nautel. We have Mr. Jamin Barrett, who is the NX Design Lead, and the guy most responsible for the development of the NX series. And we have Mr. Wendell Lonergan, who's a sales manager, regional sales manager for the Mideast and North Africa. Now, gentlemen, make sure that everyone can hear you here. Jamin, good morning.
Good morning.
Or good afternoon in Europe, I guess, and other parts of the world. And Wendell, good afternoon or good morning.
And good afternoon to my friends in the MENA area.
I would like to talk about a little bit of history for a second, Mr. Lonergan. How long have you been with Nautel?
30-plus years.
And in most of those years, you had a role more similar to what Mr. Barrett does today.
That's correct. First 25 years of my life was in research and development, and prior to coming to sales, I was the AM project leader.
Wonderful. So the long history of reliability that Nautel has is in part due to your own efforts.
Well, I like to think so.
So let's talk about what we're going to talk about today. We're going to talk about an overview of the NX series. We're going to talk about how the NX series handles digital. And today that means HD radio in some parts of the world and DRM in many parts of the world. And we're going to talk about the control aspects of Nautel's NX series. And then we're going to actually take you down into the test room virtually and bring you on a live tour of an NX transmitter that's running down there into an interesting load, into a load that has real antenna characteristics. We're going to talk about NX clusters. We're going to talk about how we can expand the NX series from the 100 kilowatt level on up to as high as 2 megawatts. And we're going to talk about taking the NX series to long wave. In many parts of the world, long wave is a very viable broadcasting band, and the NX series now has a model, a series of models which works in the long wave band. And then to pull the whole package together, we're going to talk about Nautel system integration. From a historical standpoint, I would be remiss if I didn't mention that this is Nautel's 40th anniversary. Nautel started in 1969 building nothing but solid-state transmitters. We've never built a valve transmitter in our life. On the left side, you can see some of the early founders. Wendell, you're not in that photograph, but you would have been a kid, I guess. And on the right-hand side, you can see when we introduced the very first solid-state AM transmitters in 1972, I believe that's right.
Yes.
And you can see our building here on the shores of St. Margaret's Bay in Nova Scotia in Canada in the lower right-hand corner. Today, this is pretty neat. This photograph here is the NX design team, the engineers that developed the NX series. In total, Nautel has about 37 design engineers, I believe. Jamin, is that about right?
That's about right.
And you can see on the right-hand side, all the little gold dots are where all the Nautel transmitters are located in the world. And they're just about everywhere. So let's talk about the product families that Nautel has. On the lower left-hand corner is our new VS series, a low-power FM series, goes from 300 watts to 2.5 kilowatts. And on the lower right-hand series, we have our NV series of solid-state FM transmitters going from 3.5 kilowatts all the way up to 88 kilowatts, and groundbreaking in many ways. And on the top is our subject of today's conversation, the NX series, which is available from the 25 kilowatt level all the way through up to 2 megawatts. And all of these are tied together. They all share the AUI, which is our advanced user interface. They're all accessible by the web, and you can get at tremendous amounts of information and data and control with a built-in web browser into every one of these transmitters. Let's talk specifically about the NX series. You can see the various models here, and there's a lot more. You can get virtually any size you want, from 100 kilowatts up to 2 megawatts. The industry's top efficiency, 90% efficiency, AC in to RF out. These are the first transmitters at high power to feature adaptive pre-correction, the ability to change the way that the signal is amplified and created so as to compensate for nonlinearities in the system. We have both RF and audio spectrum analyzers. The modulation works at 2.77 megasamples per second. It's direct digital modulation. That's very important for modulator bandwidth. There's the intuitive touchscreen interface. They're ultra compact, and they handle all DRM modes plus HD radio. Here is the actual size of the 100 kilowatt transmitter. You can see the sizes there. Actually, one of them I'm not seeing, but it's about 6 feet tall or something like that, I guess. The NX25, the NX50, and the NX100 all have the same size cabinet. It's just that the NX100s and above have a small external transformer cabinet which can be mounted either adjacently to the transmitter or remotely, so that the AC transformer can be mounted remotely. This shows a kind of internal view of the NX series. Jamin, these are the modules. In 100 kilowatt, you have 40 plug-in modules.
That's correct.
And then up here is the output network.
That's correct as well.
At the top, you can see some of the power supplies and things in here. And this is a back view, and you can see here, this is what the also part of the output network.
That's correct. We have a double T output network, and those are the shunt capacitors.
Wonderful. And down here you can see some of the power supply components in the lower right-hand corner. All right. There's a block diagram of the NX100. Jamin, would you like to walk us through here the NX100 block diagram?
Sure. So the NX100, we accept audio inputs, various audio inputs, whether they be AES, EBU, your standard analog input. Obviously, there's the TCP IP control, so you can see any of the stuff that we're going to be showing you today remotely for your systems. Through there, we've got our main control supervision section. That's the interface for the exciters as well as the user interface. It distributes all of the control signals and the monitoring over RS422 types of interface, where we will send the mod drives as well as the RF drives to the modules, as well as so the modules are all 2.5 kilowatts. Depending on the power level of the system, the number of modules will vary. The modules get combined through a series combiner, and then the output network, which we were showing some pictures of there earlier, is a double T output network. The mains transformer, the AC comes through transformer. That's good for lightning protection, the decoupling through the transformer. So we've got large mains transformers which take the voltage and will rectify it through a SCR style rectifier, and it's a choke input filter.
And all the other lower voltage power supplies are redundant.
That's correct. They're all redundant, and they're all in the secondary of the mains transformer, which again provides isolation from the actual mains, again meaning better lightning protection and so on.
Then we have, this is actually a 17-inch LCD, isn't it?
It is a 17-inch
LCD. Screen here. A 17-inch touchscreen LCD, and then we also have here the capability for optional GPS.
That's correct.
And we have the ability on the controller card to provide manual control.
That's correct. And I think it's important just to note that some people get scared from the LCD display saying, what happens if the monitor has a problem or so on. That manual control is always there. It's all embedded, as well as all the LCD-based things. It's all embedded. But the manual control is a backup embedded control to provide control in any situation.
Great. Let's talk about dynamic pre-correction. The NX series of transmitters is the first high-power AM transmitters to be provided with dynamic pre-correction. And this shows the schematic of the dynamic pre-correction.
That's correct.
And go ahead.
Oh, sorry. I guess the good thing to point out is in designing the NX, we put a lot of effort into getting good digital performance. And in doing so, we spent a lot of time trying to make sure the transmitter was as linear as possible without doing any correction. What the correction does is it then just puts another layer benefit to the system where we can really do things that could never be done before. So some of the things that we do, if we look at the bottom there, we do adaptive envelope equalization. So what we do is we look at the modulator bandwidth, the signal coming out of the modulator, and we will adjust the delay to compensate for group delay things, or we'll adjust the envelope, so effectively the equalizing, in order to give a flat response. The AM to AM will allow us to get incredible distortion levels, and you'll see some pictures later where we get below 0.05% distortion for a 1 kilohertz sine wave. It's just really amazing to the level that it cannot be measured. And then the adaptive AM to PM correction allows us to compensate for the Miller capacitance of the FETs and so on to get rid of that AM to PM and allow you to get good digital performance as well as sequom stereo AM performance.
And the key here about this schematic is really looking at the fact that we're actually sampling with a directive coupler the output of the system through an analog to digital converter, and then looking at comparing that with ideal and then figuring out what changes need to be made.
That's right. The neat thing is you can do this in the field to get even better performance. You can do it into a standard reject or dummy load and get very good performance, but there's been a few times that I've gone in remotely to customers and been able to recapture some of these curves in order to try and get even better performance for them with great results.
The advantage there is that a transmitter acts differently depending on the load that it's going into.
That is correct.
Okay. Now let's talk about the pre-correction principle. So a straight line here would be total linearity, and in a typical amplifier might have some nonlinearities represented by this left line here. And what we do is in the exciter we develop a mirror image of that nonlinearity, and between the two we end up with a perfectly linear system.
That's correct, and this applies to both the envelope response as well as the group delay, so there would be a similar curve for each of those systems.
Okay, and I'm not going to go through the math. Now these show some of the curves. This is the AM to AM curve. This is what we were talking. Correct me if I'm wrong. In the years past, the knock on a PDM or PWM transmitter has been something called PDM nipple.
That's correct. The pinch-off that you see in the trough at very high negative modulation
and that's
levels.
This area here.
That is exactly what that is.
And that's why we can do this.
That is what we can do now. You'll see that there is next to no distortion in the trough.
And that's really an incredible thing because people are always trying to get that maximum modulation but without adding distortion. And this solves that problem completely. Okay, here's the AM to PM correction. This is the Miller.
The Miller capacity in the PA FET. So as you get larger, more efficient FETs, this AM to PM becomes more of an issue. So you have to correct for it, and we've been able to get better AM to PM with this correction results than has been achieved in any transmitters that I know of. So.
And Jamin, now the AM to AM, or AM to PM, and phase correction and all that are not terms that represent what the broadcaster will see in terms of improved performance. How does this turn into improved performance on the part of what they would see?
Well, what you see is, especially when you're thinking of digital, whether it be IBOC or DRM, when there is a lot of phase noise, meaning at low output voltages, and meaning in the trough of modulation, if you get a phase shift, that results in out-of-band emissions.
Right.
So this AM to PM correction will improve or reduce the out-of-band emissions. Or in the stereo world, it has to do with stereo separation. So again, with poor AM to PM performance, you do not get good stereo separation. So you can see through our specs that our stereo separation is much better than a lot of the other systems that are available today.
Okay, so for those that are running digital, whether it's DRM or HD radio or what have you, what you're going to see here is not only improved spectral performance, but possibly even the ability to lock on a signal at a weaker signal level because the signal is cleaner.
That's correct. There's less noise introduced.
And in fact, we've heard anecdotally from customers that both in HD radio and in DRM that we provide that when they're using our transmitter, they get better performance than they had with other earlier designs.
That's correct. And it's a combination of our transmitter's linearity due to some of these corrections as well as the chain that we use to develop the signals, because we can go, and we'll get into this a little bit more later, but the process that we use for IBOC is different than some of the competition, so we have less processing stages.
Great. Okay. Now this shows the modulator response. You can see the very, very broad modulator response, and here you can see this is the equalizer that's in place, and this is the modulator filter, and so the final end result is the red line. Is that correct?
That is correct.
Okay. And this is the group delay of the modulator response. So you end up with, again, the equalizer is here, the modulator filter's response is here in terms of group delay, and the end result is an almost perfect group delay performance.
That's correct, and these aren't just mathematical pictures. These are things that we've proven out, and we've seen the actual results of the transmitter show what you see there exactly. So
these are just like right out of a textbook, aren't they?
That's right. That's right. It's really exciting when you can design something and work through it and see the math for it, but then actually see it work in the system and see the benefits of it.
Yeah. Okay. Let's talk about the antenna considerations. A transmitter can produce the RF, can put 2 megawatts into an antenna, but the antenna is not a resistive load. The antenna is a complex load, and many broadcasters who have made the transition to CQAM AM stereo and eventually on to digital have learned to respect the changes that the antenna system can make.
That's correct, and it's important to realize that a well-designed antenna is still an important part of the system.
So there's a sweet spot, isn't there? If you look at a Smith chart like this one here, this one is an ideal antenna cusp, as we would say. This is a response from the high end of the spectrum we're modulating to the low end of the spectrum. It's showing the response on a Smith chart.
That's correct.
And if it's rotated the wrong way, it could cause distortion and out-of-band performance that we don't want.
That's correct. Because a transmitter is a voltage source, it's fairly well accepted in the industry that the correct cusp is trying to present the PA with a parallel tuned load, which in this case would be a load oriented to the left or the 9 o'clock.
Okay. All right. We'll see this live. We're actually going to do this live, right?
That's right.
All right. So let's talk about the controller card. This is the main card of the transmitter. We've got all our audio inputs and outputs up here. We've got our control. The interfaces, the dual DSP exciters. We have 2 AES EBU inputs, analog left and right, and INQ inputs, native INQ inputs. That's not standard on most people's transmitters.
That's correct, and we actually have 2 INQ inputs on this system, which is beneficial when you're trying to do simulcast or having various schedules modes set up.
Okay, and we have an optional GPS card we discussed earlier for the ultimate frequency accuracy, and probably also the possibility that there are people out there that would like to do synchronous AM broadcasting.
That's correct.
And we have the parallel remote control, a full web server, and a fail-safe manual basic control. Correct me if I'm wrong. These are the optos out here?
That's right. The manual control.
The push buttons are right there, aren't they?
Well, there are a number of push buttons on that board itself to provide a small amount of control, but the user can then extend it. On the right side, you can see a digital interface card can be installed, and that will provide 16 buttons and 16 lights that can be configured. And there's little white sections where you can write in your own language, if need be, certain controls or commands that can be configured using the AUI.
Excellent. Okay, so these are the redundant DSP exciters, direct to digital. They use an embedded DSP FPGA system. They provide a full digital system from source through to modulator and the power amplifier. And they accept INQ signals from the DRM exciter or HD radio XGM card.
That's right.
Okay, and what is this one? This is a very interesting looking heatsink. I've always wondered what that is.
Well, that's on the FPGA.
Okay.
All right.
And this is where the adaptive transmitter linearization goes on. And we have iBox signal conditioning going on here by moderating the high frequency phase transitions inherent in the iBox signal.
Yep.
So that improves the performance of the transmitter. And then the antenna equalization capability is here as well. Okay? Let's look at a modulator, or rather an RF amplifier module, which includes both the RF output amplifier and the modulator. This device is actually 98% efficient.
It's actually slightly more efficient than that. It's just above 98%. It's really a step forward in efficiency.
I have seen one of these things myself operating continuous CW signal at over 12 kilowatts for long extended periods of time.
That is correct.
And we only use them for 2.5 kilowatts of average carrier power.
That's right.
Okay, so there's a lot of headroom in these things. And the interesting thing here is these 4 field effect transistors right here are 200 ampere FETs, and they can be replaced with just a screwdriver.
That's correct.
And part of the reason for the efficiency of this module is because those are such large FETs, so they're not really running hot.
That's right. It's a dual. We're at the place where our module is so efficient that there is no switching loss. We do some very special things with our drive signal to improve our efficiency, and the only loss is conduction loss, and the conduction loss is very low because the FETs have such high current ratings.
That also adds to the reliability of these modules too, obviously.
And interestingly enough, yesterday I just did a reliability analysis on the module based on field feedback, and the module comes in at just over 2.5 million hours.
Wow.
For an MTVF, which is pretty fantastic.
That's wonderful. That's wonderful. Here's an actual basic schematic, just a highlight of the amplifier modulator. So you have the modulator stage over here. Now the transmitter as a whole uses 9-phase modulation.
That's right.
And there are 3 phases present on every modulator, on every module.
That's right.
So you have 3 modulators operating, what would that be, 120 degrees out of phase.
That's right.
And then you have the RF amplifier stage, which is a standard Class D H bridge.
That's correct.
Okay, and the output is coupled from here. Anything else you'd like? All of the inputs to all of these RF drive as well as to the modulator drive is all sent through an Ethernet cable from the exciter.
That's correct. We find that the RS-422 standard balanced signal is a very robust signaling mode. So we use that signaling mode to transmit the RF drive and PDM signals from the exciters down to the modules themselves over an Ethernet cable. And as Chuck was mentioning, each module does have 3 PDM phases that are 120 degrees out of phase, and then each module is 40 degrees out of phase from the previous module, and that's where we get the 9-phase of cancellation.
That provides that's where we get the tremendous bandwidth of the modulator.
That's right. Because we've got such a large number of phases, we can increase the modulator bandwidth and get cancellation that's inherent from having 9 discrete phases.
What's the benefit of these silicon carbide rectifiers here?
Well, there's effectively no turn-on. They turn on extremely quickly, and the loss is next to gone. It's very, very low loss. Maybe, yes, that's the benefit, is the reduction in loss.
Okay, thank you. This is the side view of this modulator module, or amplifier and modulator module. These amplifiers are completely broadbanded. There's no tuning, no adjustments, no component changes for the entire AM band.
That is correct.
And they're hot pluggable.
And there's several benefits of that, whether it be through frequency change or whether you own more than one NX transmitter. You don't have to spare or depot multiple units tuned for different frequencies. It's just that one unit.
So if you're a large network and you have transmitters of all kinds of power ranges from 2 megawatts to 25 kilowatts, this is your spare module.
That is correct.
And it goes into any one, regardless of frequency.
That's correct.
Very cool. So this is looking at the front view. This is the RJ45 where all the input signals come in. And the LED, what is that? That's a tricolor LED. What do those tricolors mean?
Well, the tricolors are used to signal different things to the user. Whether it be red or red, yellow, or green, it tells you the mode of the module.
Okay. All right. And this is where the distribution of all of those drive signals, the RF and the modulator drive signals, goes out from the exciter to each of the modules.
That's correct. What you see there is the distribution of the PDM. So the PDM comes into this board and it distributes it to the 40 modules.
Excellent. And then this is the series combiner. This is also broadbanded. There's no frequency adjustment to this at all.
That's correct.
All right. And then this module isolation relay is one of only 2 moving parts in the NX. The other is the fans.
That's correct.
Pretty cool.
Yeah.
All right. And then this is the output network, which is the only frequency-dependent section in the NX series. It consists of 2 T-networks with a shunt third harmonic trap. It's a low Q filter, which provides minimal amplitude and phase distortion. and you can change the frequency from one frequency to another frequency in just a few hours.
That's correct, and because of the simplicity of a double T network, there isn't a lot of components that have to be adjusted.
And we actually give you an Excel spreadsheet. You can plug in the frequency we're on, the frequency you're going to, and it'll tell you what to change.
That is right.
Okay. This is showing the tank coils inside.
That's correct.
And then this is really neat. This is a schematic of the output network. So you can see each of the RF amplifiers here. There's the series combiner, and there's really not coils. That's a pipe, if you will.
That's right.
And then this is the twin T harmonic filter and output matching network that we were talking about.
That's right.
Okay, now the interesting thing about this is let's talk about the things that make it. Why is the reliability of our solid-state transmitters so high with regard to lightning?
Well, you take an approach where you have more and more rugged protection as you get closer to the source. So whether it be things that we recommend for sight, which is the normal ball gaps and the static drain chokes and so on, those are all things that we recommend to get the highest level of protection. But then as you come into the transmitter, you see we've got our directional coupler. So we've got protection that's on the order of less than a microsecond. So we can shut off the module very quickly, but we leave the FETs on so that they discharge the current. But then you take another step back and you've got your spark ball. So a set of spark balls that will be set up appropriately is a very good level of protection.
The carbon ball gap, and then you have the fast spark gap, the pressurized tritium gap.
That's correct, and that responds very, very quickly.
But another thing that's quite, I think, unique is this high pass section. The studies show that lightning's major components are in the less than 100 kilohertz region. So if we have a series high pass, then we pass the AM band and notch, in essence, the lightning part of the band. So
That's correct.
Okay, so that solves a lot of problems. And plus, of course, the fact that if you look at this schematically, if I can make this work, that's a pipe going straight to ground.
That's right. That's right.
That also helps. All right, and this just shows the photographs of the things we were talking about. There's the tritium gap. There's the carbon ball gaps. There's a static drain.
That's right.
And then this is showing the low pass, or the high pass filter, I presume. Right. Okay. Anything else here? MOV protection on the incoming AC is obvious, I think.
That's right. And this goes back to what I was talking about with the choke. There's an inherent amount of capacity from primary to secondary winding on the transformer. So that, coupled with some capacity that we put on the secondary, provides a capacitive divider, which is inherently a very good way to protect your supplies within your transmitter.
Excellent. Cooling. The transmitter has trays which can be pulled out while the transmitter's on.
That's right.
And you can replace the fans very, very simply.
That's correct. It's just a couple screws, removing one D sub connector, and the tray can be pulled out. And because we give metering and temperature information, if there is a fan that is slowing down or has an issue, you can know right away remotely and come to the site with a new fan tray if you'd like.
Because we're actually monitoring with a tachometer each of those fans.
That's right. You know within whatever 100 RPMs how fast each fan is running.
But because they're ball-bearing fans, expensive, high-quality fans, the life is typically over 11 years each.
That's correct. They're very high-quality fans that we've selected.
And because the transmitter is 90% efficient, only 10 kilowatts of heat in a 100 kilowatt transmitter is being produced, which is similar to a 10 kilowatt FM transmitter.
That's correct.
Okay. These are the power supplies. You've got a three-phase AC power, broad range of configurations fed through a high-efficiency transformer in a separate cabinet. And you've got the 10 large fuse banks and the filtering. And we show those photographs here. Those are the fuse banks.
That's right.
And there's the filter bank with the chokes as well. So you've got the chokes on the one side and the electrolytics on the other. Okay, and all of the low-voltage power supplies are redundant. And there's the low-voltage power supply.
That's correct.
This is talking about the digital capability of the NX series. As we've discussed, we have AM analog, we have Sequom AM stereo, DRM, and HD radio are all basically able to be built into the transmitter.
That's correct.
Okay. In terms of DRM, we use a third-party DRM exciter, and we have a technology called DRM Power Boost that can significantly increase the amount of power that you can get out in terms of RMS DRM power out of a particular power transmitter than other companies can do. Okay, and we have the ability to do simultaneous split frequency AM and DRM in one transmitter.
And that's right. And the neat thing about the way that we do that, and it is unique, is that the DRM modulator is providing I and Q data for the DRM data, and within our transmitter we can then insert the analog data. It's not done through the modulator, it's done within our transmitter, which provides a lot of extra flexibility, whether it be if there's an issue with the modulator, it doesn't take the AM signal down, and you can do whatever conditioning you want in your AM signal completely separate from the DRM modulator.
But if you think about what we're asking the transmitter to do with having an adjacent frequency, the adjacent channel have analog and then DRM in the other channel, that requires a lot of modulator bandwidth and a lot of linearity.
It sure does.
And that's why we can do this. Okay, on the HD radio side, it's super simple. You can put your XGen card right inside the transmitter, feed the LVDS signals digitally to the exciter, and there's no mag phase amplitude or phase adjustments at all required in the NX series.
That's right.
Which is, having done that at 2 o'clock in the morning, that's no fun.
Well, it makes it a lot easier just to have one variable that you're adjusting rather than two. And even the one variable that you do adjust, which is the delay, not the amplitude, but the delay adjustment, it's a very simple one because we know what the delay should be.
Okay, yep. Multiple levels of control. The transmitter has a 17-inch color LCD, a wide range of configurable displays, touch screen control or mouse and keyboard. There's instrumentation built right into the transmitter, including a network analyzer, a spectrum analyzer, monitoring control of all functions to the module level, logging of all functions, and all of this is available via the web. You can get at it from any place. If you put an internet connector, a router on your transmitter, then even from your smartphone you can access the NX series transmitter. Okay. We talked about the built-in built-in instrumentation. And we'll actually show you all of this in this next screen. In fact, let's go ahead and do that now. Let's go back over here and switch over and go to this. There's our transmitter downstairs in the test lab. This is a 25 kilowatt transmitter?
That's correct. Well, this is actually a 50 kilowatt transmitter.
Okay, running at 25.
The test load that we're running into is only capable, the antenna simulator is only capable of 25 kilowatts, and that's why we're operating at this power level. Fair
enough. So we are operating in analog AM mode at 700 kilohertz right now. And you can see here on the spectrum analyzer that we're operating obviously well inside the spectral mask. We can actually take this spectrum analyzer up to full screen. Now this is 100 dB top to bottom, and it's 100 kilohertz. No, I'm sorry. It's let's see here, 625 to 775, 150 kilohertz in width. All right. So, and we have on here we have all of the measurement tools. We can set a marker here. We can change the kind of spectrum analyzer, I believe.
Well, in this particular one, you can see here you can adjust your span and your bandwidth resolution, your averaging rates, and those things all get set up automatically based on the operating mode.
Okay.
So, and you can modify them, but the interesting thing is whether for DRM or IBOC, there's always different suggestions by the different consortiums on how to set them up, so we automatically set it up at the recommended mode.
So that you can see relative to the recommendations from DRM or HD radio or
where
wherever
you stand with spectral compliance.
Okay, all right, very good. Let me bring that back down. Now we have a lot of other tools in here. If I can get rid of this modulation levels, I can bring up the toolbar, and you can see all of the tools that we have that we can look at. We can look at the equalizer frequency response. This is more or less a graph that we saw before. This is generated by the transmitter, and it's what's providing us the perfect modulation. It's the antithesis, if you will, of the normal modulator filter delay, or
amplitude response.
Yep. Yeah. Okay. So let's go back and put that back into modulation. Where am I going to go here? There we go. Modulation. All right. Let's change modes. Right now we're in analog AM, but let's see how hard it is to go to DRM. Oops, sorry. Do it over here. Do it load a preset.
So we've already created a DRM preset, and we can show you what we do to set that up. It just makes it a little quicker.
Okay. So now we've switched to DRM, and we are actually in DRM mode at the moment. And That's how quick it was.
That's right, it's that quick. It's a matter of, in order to run from DRM, you just tell the exciter that you want to operate at DRM and tell it where the AES input is coming into the transmitter. So you plug it in, and right now we've plugged it into the digital I&Q AES input. We tell the transmitter that that's the input, we set up the level appropriately, and bang, you're in DRM and it's operating.
Cool. Now, I could actually not have to go into the web interface or anything to do that. I could have actually just gone in and utilized our built-in scheduler, because what we've done then is we've said, okay, this particular station wants to operate every day from 11 to 12 in DRM mode, and the rest of the time be in analog mode. So the scheduler is automatically taking care of that.
That's right, and the interesting thing that we've done here is rather than forcing you to do exciter A for DRM and exciter B for analog operation and setting up maybe a remote input to switch at a certain time of day, you don't actually have to use the different exciter. You switch modes and you still keep your redundant exciters, whether you're in one mode or the other.
Awesome. Okay. Now let's go ahead and let's be really difficult, and let's go in and load analog plus DRM simultaneously. Okay, so now we are in analog plus DRM, and if I zoom in and make this full screen, I can actually see here's my analog signal, and here's my DRM signal on the adjacent channel.
That's right.
Pretty cool. Pretty cool, and we're still meeting the mask.
That's right, and this is into a reasonably challenging load. It's 1.5 to 1 VSWR at 15 kilohertz.
Let's talk about that for a second. Can we go ahead and do that right now? Let's talk about, is this the right time to do that?
Well, it might even be better when we're in IBOC to have a look at it.
Okay, let's switch over to IBOC, just for grins. While we're switching, let me ask you a question. Could you actually, not that anybody'd ever want to do this, but could you actually switch from HD, could you have HD radio and DRM both located in the transmitter and switch from one digital mode to the other?
We just did it.
Yeah, you're right. But I mean, wow, you're right. We just did. You're right. All right, so there we are. Now let's zoom in on this, bring it up. This is a Smith chart, which is actually showing the performance of the transmitter within the real modulation. We're not taking the transmitter offline and adjusting it or anything like that. We're measuring tone. This is actually with real modulation going on here.
That's right, and that's why when we switched to operating modes, you can see that the cost changed in the amount of frequency content that was present. And the reason why I suggested we wait for IBOC to do it is because there's the most frequency content in an IBOC signal.
Sure.
So if we were to right now switch to analog AM, you'd see the cusp shrink.
Right.
And that's because there's less frequency content available.
Less diversion of the audio.
That's right. Instead of, right now we're operating with plus and minus 15 kilohertz. If you switch to analog AM, it would be 5 kilohertz.
So this is a real network analyzer. I just highlighted a spot on the curve here, and I can see the impedance and the frequency. We're 7.5 kilohertz down from the carrier frequency, and that's the actual measured performance.
That's right.
Okay. Now, can we have somebody twist, or can we not? Is that not possible?
We can. I'd have to call someone down to the test room and get them to
The bottom line is that if we were to adjust the antenna, that's all right. If we were to adjust the antenna so that we change the performance of the antenna, we would actually see it fall outside the spectrum mask.
That's right.
Okay. Okay, go ahead. Let's go ahead and do that real quick. Wendell, let's talk about the meters here.
Sure.
We've pulled up from this menu here various meters. We've made several choices, and those are now displayed on here. And we can choose anything we want.
We can, and what's really cool is the fan tack measurement.
Let's go get a fan tack measurement. I'll turn off the PA volts here. Don't even have to do that, really. I suppose I could just go grab, where is it? Fan 1 speed. There it is. Okay, so now we're seeing that the fan 1 on cube 1 is running at 4,260 RPM.
Right, so if you had a system where your fan filters were very dirty and causing a lot of back pressure on the fans, you would see the fan's speed would start to drop back a little bit, and that would be an indication for your maintenance crew to go out and clean your fans up.
Okay.
So it's a great great routine maintenance tool so that you can be proactive instead of reactive.
And can we set up the ability for the transmitter to actually notify us if something falls out of a particular variance? Oh, the Smith chart's changing. Yep, see that? Now let's take a look at the spectral mask. As this is continuing to move, you can see here that the curves are starting to get closer and closer to the mask limits.
That's correct, and I'm not sure how far he's going to twist it here. I asked him to give it a couple turns, so hopefully it'll go far enough. Yeah, you can see the mask.
Quite some distance, yeah, you can see it now. And you can see here that we're considerably above the spectral mask at this point in time.
That's correct.
Wow, look at that. Now, I have to explain. I had a situation one time where I was at the NAB show. We were doing this exact presentation live.
Yes.
And there was a not a young man, an older man from Hong Kong who came in. I'll never forget. He came in, and I showed him this part of the thing. I showed it live as we cranked on the thing, and we saw the network analyzer, and we saw the spectral performance. And he cried. There were tears coming out of his eyes, and I said, "What's wrong?" And he says, "You don't know how many nights I've spent doing this, where it took hours and hours and hours with the OID analyzer to come up with this same thing. Yes. And you've just done it in seconds."
Yeah, and we've done it accurately because we're taking the signal from this directional coupler, regardless of the line length and VSWR on the antenna. We are actually seeing the true analysis of the network.
That's right, and so what you see there for our spectrum analyzer, it matches very closely with the far field measurements and the near field measurements, rather than just picking a voltage or a current sample.
That's outstanding. And in fact, to carry this incredulous thing one step further, everything I'm doing here I could do from any place on the planet.
That's right, and we have.
Yeah, that's right. Okay, anything else we want to show here? Anybody else got something else that they would like to?
Oh, you did talk about things going outside the normal operating condition and notifying somebody.
Yep.
In fact, you can set up parameters that it will send you an email and say, "Hey, there's something not quite right here."
Isn't that cool? And you can configure that to be what you want to.
Absolutely.
All right. So just because one fan slowed down doesn't stop your steak dinner.
Of course not.
Not necessarily.
Well, we haven't talked about the headroom in the transmitters. We talked briefly about the reliability, but if you lose a power module in a 100 kilowatt transmitter,
yep,
the transmitter actually has a science to look at it and determine that without causing undue stress to the remainder, it will actually readjust the power back to its normal rated power.
And in fact, we had a scenario like that in a 50 kilowatt transmitter in San Francisco, if I recall recently, where Kevin Rogers, our head of customer service, was logged in on a weekend to a transmitter, and he noticed that there was a problem with one of the modules. The station had no idea they had a problem. He dispatched a new module out of our depot in Memphis, Tennessee, to the station, and they got the module before they knew they had a problem.
That's right. And because we do have closed-loop power control, we can do that. We can increase our power or decrease. It's not open loop. So when a module does have a problem, if it's running at lower power or reduced power, we can increase the transmitter power to compensate and maintain coverage.
Wonderful. Okay. Let's see here. Let's go back and take a look at the PowerPoint presentation again. The next point I wanted to get to, if this will advance. There we go. These are some features that we're working on. They're not ready for prime time. May look a little different than this when we finally get into the final version. But we have something called AUI Anywhere. This is the ability of a transmitter to, in essence, look at and monitor other transmitters that are part of its same network. We can envision two situations. Number one is a group broadcaster has many stations, and they have many NX and NV series transmitters and NVS, and they can actually monitor their other locations. So a transmitter engineer is typically spending time at the transmitter site. He has the capability of seeing the status of his other transmitters in his network. And if he clicks on one of these call signs here, let me see if I can get that. If he clicks on one of these, it'll actually enlarge and show them the actual AUI screen from that station. And then down here we have the capability of putting an audio processor right inside the transmitter. We've worked out a deal with or band, and we have the ability to put a DSP audio processor running their code right inside the transmitter, and that gives us the capability of adjusting that right on the AUI. So that's coming as well. Let's talk about how the NX series expands. We've talked about the 100 kilowatt. Let's talk about how we can scale this up to 2 megawatts. Jamie?
Okay, well, we've got lots of different methods for doing so. It really depends on customer requirements. But right now, our high-power building blocks, as it says there, are the 100, 200, 300, and 400 kilowatt systems.
Those would be what's called single-ended.
Single-ended
There's no combiner associated with those.
That's correct. They're just single transmitters. And we can combine any combination of those in order to get higher power systems. So if you wanted a 2 megawatt system, you might take 5 400 kilowatt transmitters and combine them. And in that combiner, you can then say, well, I want to take one out of service. I want to run on 4 of them. Or you want to take 2 out of service and you want to run on 3 of them. Or you can take 1 out of service and run into the reject load. So it's a completely redundant system in that you can configure it. It's a fully switched matrix.
Because of the other half of one of these high-power systems is how you split the drive signals to the transmitters. How do we do that here, and why does it work better?
Well, the interesting thing is, because of the way that we design our system, each system will have its own drive signal. We just have to time them. So we'll have a GPS-based solution that will provide a timing signal, both phase and frequency, to the transmitters, and the transmitters then can just operate off their own internal exciters, which provides additional redundancy because you don't have a single exciter.
You have a single point failure in the system.
And you can then duplicate that GPS timing source. So if the timing source does have a problem or fail for some reason, the transmitters will all decide together, look, let's switch to the other timing source. And then upon switching, it'll be all operating normally.
Okay, very good. So this is graphically what an 800 kilowatt looks like. You've got an NX 400 here, so the 4 cabinets. You've got a larger cabinet here, which is the combiner in the middle, and then you have another 4 cabinets over here.
And that's correct. And what you don't see on that picture is on the combiner cabinet, we will be placing a 17-inch AUI on that as well to control the system. So you'll get summary information within the combiner itself of the status of each of the individual transmitters.
One big thing I forgot to mention is that the AUI is multilingual.
That is correct, and we've already done translations to various languages, whether it be Turkish or whatever.
So meaning to say, everything we saw on that screen could be in Turkish, for instance.
That's correct, and it's a fairly easy thing for us to do because of the way that we've designed the system. It's a matter of translating an XML file, and then you can incorporate it for other languages.
Okay, so a 1.2 megawatt system would be 3 400s combined, and a 3-way combiner.
That's right, or 4 300s.
Okay, and then this 1600 kilowatt.
That would be 4 400s.
And a 2 megawatt system would be 5 400s.
That is correct.
Okay, seems realistic. This is some of the work, Jamin, that you've done on the combiner design. Can you decipher these for us?
Well, this is a fairly crude drawing, just showing what an 800 kilowatt combiner would look like. So just for scaling, it's about 7 feet by 9 feet and about 6 feet tall. And in there you'll see a reject load, so there's 16 muffin fans there that are blowing air over some ceramic resistors. And the actual combining system is fairly simple in that with the combined system we do a high-passed network where there's a series capacitor shunt inductor for each input. And what you see there is the reject load in series with another inductor to provide better than 30 dB of isolation between transmitter input ports.
Okay.
And it's a fully switching system, meaning you can go A plus B into the antenna, A plus B into the dummy load, A into the antenna, B into the dummy load, or vice versa. So you can use it as main standby as well.
Okay. And how about this drawing on the left?
Well, that's the switching network. So it's what you see, it's upside down from what it is in the transmitter, just to give you a look at the copper piping that's used to interconnect the switches.
Okay, very good. Now let's talk about long wave. Frequency range of long wave traditionally is 148.5 to 283.5 kilohertz. These transmitters also have typically 90% efficiency, 135% positive peak modulation, and are capable of operation into a 1.5:1 DSWR.
That's correct. And the positive peak modulation can be a little bit higher than 135 as well.
Okay.
It depends on requirements.
So this shows an actual NX300 long-wave transmitter and how it looks.
That's correct.
Okay. Let's talk about integration services. Wendell, you've been very involved with this. The larger systems, the megawatt transmitter sites, oftentimes require more than just shipping out a box, don't they?
Oh, absolutely. Absolutely. They've gone full scale from requiring buildings to just doing systems inside. But we work with partners for antenna services, for air conditioning services, and put together a dedicated team working out of Nautel, Canada here with our own project managers.
We have project managers. We've worked with other companies in terms, particularly when there's civil works involved and building roads and buildings and things like that. And we have Steve Schmidt down in our Quincy office that is a master of integrating third-party products.
Absolutely.
We send our engineers, Jim Kruger is a veteran in this industry in high power AM, and we send him out on site surveys from time to time, and he gets his flight miles.
That's right. He's pretty well written a book on site surveys.
We've also done a lot of work with international financing. We work with EDC in Canada, Economic Development Canada, provide funding packages to make it easy for our customers to make the purchase.
That's right, absolutely.
And we can offer the soup to nut solution or microphone to antenna solution.
Full meal deal, absolutely.
Okay, all right. This is showing some of the installations we've done. This is actually what, Sri Lanka, isn't it?
Sri Lanka is in the top left.
Okay.
9 3/16 rigid line.
Mm-hmm.
Considerable challenge.
How long has that been on the air in Putlam, if I recall, for Trans World Radio?
Must be 6 or 7 years now.
Yeah. Okay, that's a 400 kilowatts.
400 kilowatts.
Okay. And then what's the top middle here? You remember?
I think that's Sri Lanka as well.
Okay.
That whole slide is Sri Lanka.
Okay, the whole slide is Sri Lanka. Okay, right. Putlam. All right. And that one was actually a pretty interesting situation because it's right on the sea and there's a lot of ocean air and things. So we had to do some special things to help the customer resolve some situations there.
Absolutely.
Okay. Where's this one? This is a beautiful location. Goodness gracious, gleaming.
Kuwait.
Is that right? Look at that. You could eat off that floor. That's just gorgeous.
It's marvelous installation.
Okay. How long has that one been on the air?
2000, so.
9 years.
Yeah.
And this one is what power level?
That's 400 as well.
Also a 400 kilowatt. So this is a 300 kilowatt. Look at the size difference. This is a 300 kilowatt in what, Turkey, isn't it?
That's in Turkey.
Which city is that in?
That's either Mersin or Trabzon.
It must be Trabzon.
Yeah.
Okay. All right. So that's the whole thing for a 300 kilowatt transmitter. There's another 300 in Turkey?
Yeah, that one's in Mersin there.
Okay. All right. All right. Now these are...
That's a typical beautiful installation that you'll find through National Grid in the UK.
Okay.
There's several of our systems running there.
Looks like two 100s here.
It's a main standby NX100 for BBC Radio 5 in London.
Wonderful, wonderful. And how about this? These are in an Asian country, if I should say. Two 300 kilowatt transmitters recently installed. Here you can see the transformer cabinet behind the 300, and you can see the wiring ducts that are bringing the wires across that interconnect the transmitters with the transformer cabinet.
That's right. It makes a very nice, clean installation.
Very professionally done. Yep.
Absolutely.
Okay. Let's talk about the dummy loads. Most people, I suspect, don't have any clue that Nautel makes dummy loads.
That's right. We make 100, 200, 300 kilowatt dummy loads.
Right. Okay. And this is a 200. They're usable either indoor or outdoor. They're fully sealed and slanted to prevent the water penetration. They're louvered, and they're rated for, this is a question a lot of people ask. A 200 kilowatt load is actually rated for 300 kilowatts of RMS power. That's to handle the modulation.
That's correct.
They work over the entire AM frequency band and provide a standing wave ratio, VSWR, of 1.05 is to 1 maximum. And again, available in many power levels. Here shows some interesting integration. Wendell, you're actually in this photograph here.
I am, yes. That was an emergency used container that was done for National Grid Wireless to serve the UK. It's a 100 kilowatt transmitter complete with PI equipment and a dummy load inside a 20-foot container. And this is to be shipped around the UK to service a site where a transmitter has to be off the air for building maintenance or what have you. And it was, in fact, deployed to Brooklands Park when they purchased a 100 kilowatt system there.
So this is actually a 100 kilowatt transmitter with all the program input equipment, with the not a generator.
Not a generator.
But with the dummy load, and is there an ATU in there as well, or no?
No, there's no ATU, but it is air conditioned.
Okay, it is air conditioned.
It's a full power dummy load too, so you can, within that container, operate at 100 kilowatts plus mod, so for 150 kilowatts into that dummy load.
And you can just roll up and roll out the feed line, and there you are.
That's right.
How about that? Okay, and that's only a 20-footer.
Only 20-footer.
What are the limits? What could we do?
How much power could we get?
Yeah, could we put a 300 in a 40 kilowatt, or in a 40 foot?
You can put a 300 in a 20-foot without a dummy load.
Yeah.
Yeah.
Wow. Okay. So let's summarize what we've gone through today. The NX series is indisputably the most advanced AM transmitter series available today. It's available from 25 kilowatts to 2 megawatts with unparalleled efficiency, ready for all forms of digital radio, and it's complete with powerful test equipment. And I also want to say, I'll leave this slide up to let you know who you can reach within Nautel with questions. You can send us all emails. You can talk to Wendell or myself. I've got a couple of questions I see here in the question bank already. One person is saying, is this efficiency that we're talking about, this 90% efficiency, is that total AC into RF out?
That's correct. For a 100 kilowatt transmitter and up, you are 90% efficient from AC in to RF out.
And we're willing to let people use the test equipment to prove that if they come here for factory acceptance.
That is correct.
Absolutely. Okay. And how could the transmitter work with web control? They want to understand what do they have to do on their side to make this work?
Oh, it's a simple networking task. We didn't really talk about this aspect of it, but there is various levels of protection as far as user accounts can be established. So if you want certain users to not have the full feature set of adjustments to be able to be made, you can block those out. But setting it up, it's as simple as setting any other web device up. It's a matter of plugging into a router, making sure that 2 or 3 ports are open if you're behind a firewall, and then simply giving the IP address. And you type that into the web browser, and the transmitter's web page will
And from a safety standpoint, if they wanted to use a hardware VPN, nothing's stopping them from doing that?
No, nothing's stopping you. Again, it's just a matter of you to make sure that you're able to open up the adequate ports.
And that would be very secure.
Very secure. And I've done this through hardware VPNs already. We've got one set up here at the office. And I've accessed the transmitter from home over the hardware VPN.
Another question we've got, what is 9-phase modulation?
Well, 9 phases, you've got 9 discrete PDM phases. So if you think of your standard PDM, you set 50% duty cycle, you get 50% of the B plus voltage out, that would be 200 volts. And then you vary that with the audio frequency. Well, now if you're going to want to have more edges to control on, you can have 9 different phases that are all out of phase from each other at 40 degrees, and you've got many, many more decision points, and also much better cancellation.
You cancel. There are always phases that are 180 degrees out of phase.
That's correct.
Okay.
It allows you to use the lower effective modulation frequency, switch frequency, but the effective result of it is 9 times that frequency.
That's right. So at 155 kilohertz, our PDM frequency's rate, this is where the 2.7 megasamples per second comes from, because you've got 18 decision points over that period of time.
How many modules could be failed without affecting the operation? Let's talk about 100 kilowatts.
That's right. So at 15% of your modules can be failed, and you can still get a full power with 100% modulation. So we will start to reduce the power when you can't get 100% modulation peaks out anymore. That's where we, as a standard, set it up. So at 100 kilowatt transmitter, there's 40 modules, so you can lose 4 or 5 modules is where you will start to get to the place where you would reduce. I guess 6 modules.
Okay. Can we use anybody's DRM exciter with the NX series?
That's right. All you need to do is feed I and Q. It's the most robust means to be able to send the DRM signal to the transmitter and allow the transmitter to still make use of all its correction mechanisms. So we do require an I and Q input to the transmitter rather than the mag and phase input.
It's better anyway.
It is better.
Okay.
Much
And
more
lastly, and I think you've touched on this, how do you control a high-power system? You actually have your own AUI to control the high-power system.
That's right. So in a high-power system, when we're talking about a combined system, not a 400 kilowatt, which is a high-power system as well, but in a combined system, you would control it. You can control it in one of two ways. You can control it from all of the transmitters individually, and slowly make adjustments to each one at a time. But the normal way to do it would be to use the combiner. So you could set a power level up in the combiner, and then it will send that command or request to all of the individual transmitters to be combined, or sending a mode change, again, it would send it to all of the individual transmitters.
Thank you, gentlemen. We have exhausted all the questions which have been submitted. We are right on time. I want to thank you, Jamin. I want to thank you, Wendell Lonergan, for your help here, and it's been exciting explaining the NX series to our audience. Thank you all, and goodbye from Nova Scotia.
Bye.
Cheers.